The path integral formulation of quantum mechanics is a description of quantum theory which generalizes the action principle of classical mechanics. It replaces the classical notion of a single, unique trajectory for a system with a sum, or functional integral, over an infinity of possible trajectories to compute a quantum amplitude. The basic idea of the path integral formulation can be traced back to Norbert Wiener, who introduced the Wiener integral for solving problems in diffusion and Brownian motion. This idea was extended to the use of the Lagrangian in quantum mechanics by P.A.M. Dirac in his 1933 paper. The complete method was developed in 1948 by Richard Feynman. Some preliminaries were worked out earlier, in the course of his doctoral thesis work by John Archibald Wheeler. The original motivation stemmed from the desire to obtain a quantum mechanical formulation for the Wheeler-Feynman absorber theory using a Lagrangian as a starting point. This formulation has proven crucial to the subsequent development of theoretical physics, because it is manifestly symmetric between time and space. Unlike previous methods, the path integral allows a physicist to easily change coordinates between very different canonical descriptions of the same quantum system. The path integral also relates quantum and stochastic processes, and this provided the basis for the grand synthesis of the 1970s which unified quantum field theory with the statistical field theory of a fluctuating field near a second-order phase transition. The Schrödinger equation is a diffusion equation with an imaginary diffusion constant, and the path integral is an analytic continuation of a method for summing up all possible random walks. For this reason path integrals were used in the study of Brownian motion and diffusion a while before they were introduced in quantum mechanics. Quantum action principle: in quantum mechanics, as in classical mechanics, the Hamiltonian is the generator of time translations. This means that the state at a slightly later time differs from the state at the current time by the result of acting with the Hamiltonian operator. For states with a definite energy, this is a statement of the de Broglie relation between frequency and energy, and the general relation is consistent with that plus the superposition principle. But the Hamiltonian in classical mechanics is derived from a Lagrangian, which is a more fundamental quantity relative to special relativity. The Hamiltonian tells you how to march forward in time, but the time is different in different reference frames. So the Hamiltonian is different in different frames, and this type of symmetry is not apparent in the original formulation of quantum mechanics. The Hamiltonian is a function of the position and momentum at one time, and it tells you the position and momentum a little later. The Lagrangian is a function of the position now and the position a little later. The relation between the two is by a Legendre transform, and the condition that determines the classical equations of motion is that the action is an extremum. In quantum mechanics, the Legendre transform is hard to interpret, because the motion is not over a definite trajectory. So what does the Legendre transform mean? In classical mechanics, with discretization in time, and where the partial derivative with respect to holds q, t plus I micron fixed, the inverse Legendre transform is where, and the partial derivative now is with respect to p at fixed q. In quantum mechanics, the state is a superposition of different states with different values of q, or different values of p, and the quantities p and q can be interpreted as non-commuting operators. The operator p is only definite on states that are indefinite with respect to q. So consider two states separated in time and act with the operator corresponding to the Lagrangian. If the multiplications implicit in this formula are reinterpreted as matrix multiplications, what does this mean? It can be given a meaning as follows. The first factor is, if this is interpreted as doing a matrix multiplication, the sum over all states integrates over all q, t, and so it takes the Fourier transform in q, t, to change basis to p, t. That is the action on the Hilbert space change basis to p at time t. Next comes, or evolve an infinitesimal time into the future. Finally, the last factor in this interpretation is, which means change basis back to q at a later time. This is not very different from just ordinary time evolution. The h factor contains all the dynamical information it pushes the state forward in time. the first part and the last part are just doing Fourier transforms to change to a pure Q basis from an intermediate P basis. Another way of saying this is that since the Hamiltonian is naturally a function of P and Q, exponentiating this quantity and changing basis from P to Q at each step allows the matrix element of H to be expressed as a simple function along each path. This function is the quantum analog of the classical action. This observation is due to Paul Dirac. Dirac further noted that one could square the time evolution operator in the S representation. And this gives the time evolution operator between time t and time t plus 2i micron. While in the H representation the quantity that is being summed over the intermediate states is an obscure matrix element, in the S representation it is reinterpreted as a quantity associated to the path. In the limit that one takes a large power of this operator, one reconstructs the full quantum evolution between two states, the early one with a fixed value of q, 0, and the later one with a fixed value of q, t. The result is a sum over paths with a phase which is the quantum action. Crucially, Dirac identified in this paper the deep quantum mechanical reason for the principle of least action controlling the classical limit. Feynman's interpretation, Dirac's work did not provide a precise prescription to calculate the sum over paths, and he did not show that one could recover the Schrödinger equation or the canonical commutation relations from this rule. This was done by Feynman. Feynman showed that Dirac's quantum action was, for most cases of interest, simply equal to the classical action, appropriately discretized. This means that the classical action is the phase acquired by quantum evolution between two fixed endpoints. He proposed to recover all of quantum mechanics from the following postulates. The probability for an event is given by the modulus length squared of a complex number called the probability amplitude. The probability amplitude is given by adding together the contributions of all paths in configuration space. The contribution of a path is proportional to, where S is the action given by the time integral of the Lagrangian along the path. In order to find the overall probability amplitude for a given process, then, one adds up, or integrates, the amplitude of postulate 3 over the space of all possible paths of the system in between the initial and final states, including those that are absurd by classical standards. In calculating the amplitude for a single particle to go from one place to another in a given time, it is correct to include paths in which the particle describes elaborate curlicues, curves in which the particle shoots off into outer space and flies back again, and so forth. The path integral assigns to all these amplitudes equal weight but varying phase, or argument of the complex number. Contributions from paths wildly different from the classical trajectory may be suppressed by interference. Feynman showed that this formulation of quantum mechanics is equivalent to the canonical approach to quantum mechanics when the Hamiltonian is quadratic in the momentum. An amplitude computed according to Feynman's principles will also obey the Schrödinger equation for the Hamiltonian corresponding to the given action. The path integral formulation of quantum field theory represents the transition amplitude as a weighted sum of all possible histories of the system from the initial to the final state. And Feynman diagram is a graphical representation of a perturbative contribution to the transition amplitude. Concrete formulation, Feynman's postulates can be interpreted as follows. Time slicing definition equals, for a particle in a smooth potential, the path integral is approximated by zigzag paths, which in one dimension is a product of ordinary integrals. For the motion of the particle from position z at time t to xb at time tb, the time sequence can be divided up into n+1 little segments tj at tj1, where j equals 1. n+1, of fixed duration. This process is called time slicing. An approximation for the path integral can be computed as proportional to. Where is the Lagrangian of the 1D system with position variable x, t, and velocity v equals a, t, considered, and dxj corresponds to the position at the jth time step, if the time integral is approximated by a sum of n terms. In the limit naa, this becomes a functional integral, which, apart from a non-essential factor, is directly the product of the probability amplitudes to find the quantum mechanical particle at τ in the initial state Xa and at Tb in the final state Xb. Actually is the classical Lagrangian of the one-dimensional system considered, also. Whereas the Hamiltonian, and the above-mentioned zigzagging corresponds to the appearance of the terms in the Riemannian sum approximating the time integral, which are finally integrated over x1 to xn with the integration measure dx1. dxn, xi florin j is an arbitrary value of the interval corresponding to j, for example its center, /2. Thus, in contrast to classical mechanics, not only does the stationary path contribute, but actually all virtual paths between the initial and the final point also contribute. Feynman's time-sliced approximation does not, however, exist for the most important quantum mechanical path integrals of atoms, due to the singularity of the Coulomb potential E2 per Rankine at the origin. Only after replacing the time t by another path-dependent pseudo-time parameter, the singularity is removed and a time-sliced approximation exists, that is exactly integrable, since it can be made harmonic by a simple coordinate transformation, as discovered in 1979 by a degree Smale-Hacker plus or minus Deroux and Hagen-Klinert. The combination of a path-dependent time transformation and a coordinate transformation is an important tool to solve many path integrals and is called generically the Deroux-Klinert transformation. Free particle equals, the path integral representation gives the quantum amplitude to go from point x to point y as an integral over all paths. For a free particle action, the integral can be evaluated explicitly. To do this, it is convenient to start without the factor I in the exponential, so that large deviations are suppressed by small numbers, not by cancelling oscillatory contributions. Splitting the integral into time slices, where the dx is interpreted as a finite collection of integrations at each integer multiple of I micron. Each factor in the product is a Gaussian as a function of x, t plus I micron centered at x, t, with variance I micron. The multiple integrals are a repeated convolution of this Gaussian gi micron with copies of itself at adjacent times, where the number of convolutions is ti micron. The result is easy to evaluate by taking the Fourier transform of both sides, so that the convolutions become multiplications. The Fourier transform of the Gaussian G is another Gaussian of reciprocal variance. And the result is the Fourier transform gives K, and it is a Gaussian again with reciprocal variance. The proportionality constant is not really determined by the time-slicing approach, only the ratio of values for different endpoint choices is determined. The proportionality constant should be chosen to ensure that between each two time slices the time evolution is quantum mechanically unitary, but a more illuminating way to fix the normalization is to consider the path integral as a description of a stochastic process. The result has a probability interpretation. The sum over all paths of the exponential factor can be seen as the sum over each path of the probability of selecting that path. The probability is the product over each segment of the probability of selecting that segment, so that each segment is probabilistically independently chosen. The fact that the answer is a Gaussian spreading linearly in time is the central limit theorem, which can be interpreted as the first historical evaluation of a statistical path integral. The probability interpretation gives a natural normalization choice. The path integral should be defined so that this condition normalizes the Gaussian, and produces a kernel which obeys the diffusion equation. For oscillatory path integrals, ones with an I in the numerator, the time slicing produces convolved Gaussians, just as before. Now, however, the convolution product is marginally singular since it requires careful limits to evaluate the oscillating integrals. To make the factors well defined, the easiest way is to add a small imaginary part to the time increment. This is closely related to Wick rotation. Then the same convolution argument as before gives the propagation kernel, which, with the same normalization as before, obeys a Frisch's paragraph-Dingo equation. This means that any superposition of Ks will also obey the same equation, by linearity. Defining then it obeys the free Schrödinger equation just as k does. Equals the Schrödinger equation equals. The path integral reproduces the Schrödinger equation for the initial and final state even when a potential is present. This is easiest to see by taking a path integral over infinitesimally separated times. Since the time separation is infinitesimal and the cancelling oscillations become severe for large values of a, the path integral has most weight for y close to x. In this case, to lowest order the potential energy is constant, and only the kinetic energy contribution is non-trivial. The exponential of the action is. The first term rotates the phase of I, x, locally by an amount proportional to the potential energy. The second term is the free particle propagator, corresponding to I times a diffusion process. To lowest order in I micron they are additive. In any case one has with. As mentioned, the spread in I is diffusive from the free particle propagation, with an extra infinitesimal rotation in phase which slowly varies from point to point from the potential. And this is the Schrödinger equation. Note that the normalization of the path integral needs to be fixed in exactly the same way as in the free particle case. An arbitrary continuous potential does not affect the normalization, although singular potentials require careful treatment. Equations of motion equals, since the states obey the Schrödinger equation, the path integral must reproduce the Heisenberg equations of motion for the averages of x and of variables, but it is instructive to see this directly. The direct approach shows that the expectation values calculated from the path integral reproduce the usual ones of quantum mechanics. Start by considering the path integral with some fixed initial state. Now note that x, t, at each separate time is a separate integration variable. So it is legitimate to change variables in the integral by shifting, where I micron, t, is a different shift at each time but I micron, 0, equals a micron, t, equals 0, since the endpoints are not integrated. The change in the integral from the shift is, to first infinitesimal order in epsilon. Which, integrating by parts in t, gives. But this was just a shift of integration variables, which doesn't change the value of the integral for any choice of I micron, t. The conclusion is that this first-order variation is 0 for an arbitrary initial state and at any arbitrary point in time. This is the Heisenberg equations of motion. If the action contains terms which multiply a and x, at the same moment in time, the manipulations above are only heuristic, because the multiplication rules for these quantities is just as non-commuting in the path integral as it is in the operator formalism. Stationary phase approximation equals, if the variation in the action exceeds a section by many orders of magnitude, we typically have destructive phase interference other than in the vicinity of those trajectories satisfying the Euler-Lagrange equation, which is now reinterpreted as the condition for constructive phase interference. Canonical commutation relations equals, the formulation of the path integral does not make it clear at first sight that the quantities x and p do not commute. In the path integral, these are just integration variables and they have no obvious ordering. Feynman discovered that the non-commutativity is still present. To see this, consider the simplest path integral, the Brownian walk. This is not yet quantum mechanics, so in the path integral the action is not multiplied by I. The quantity x, t, is fluctuating, and the derivative is defined as the limit of a discrete difference. Note that the distance that a random walk moves is proportional to SHT, so that this shows that the random walk is not differentiable, since the ratio that defines the derivative diverges with probability 1. The quantity xa is ambiguous, with two possible meanings. In elementary calculus, the two are only different by an amount which goes to 0 as I micron goes to 0. But in this case, the difference between the two is not 0. Give a name to the value of the difference for any one random walk. And note that f, t, is a rapidly fluctuating statistical quantity, whose average value is 1, that is a normalized Gaussian process. The fluctuations of such a quantity can be described by a statistical Lagrangian. and the equations of motion for F derived from extremizing the action S corresponding to just set it equal to 1. In physics, such a quantity as equal to 1 is an operator identity. In mathematics, it weakly converges to 1. In either case, it is 1 in any expectation value, or when averaged over any interval, or for all practical purpose. Defining the time order to be the operator order. This is called the Ito Lemma in stochastic calculus, and the canonical commutation relations in physics. For a general statistical action, a similar argument shows that. And in quantum mechanics, the extra imaginary unit in the action converts this to the canonical commutation relation. Equals particle in curved space equals, for a particle in curved space the kinetic term depends on the position and the above time slicing cannot be applied, this being a manifestation of the notorious operator ordering problem in Schrödinger quantum mechanics. One may, however, solve this problem by transforming the time-sliced flat space path integral to curved space using a multi-valued coordinate transformation. Equals the path integral and the partition function equals, the path integral is just the generalization of the integral above to all quantum mechanical problems where is the action of the classical problem in which one investigates the path starting at time t equals 0 and ending at time t equals t, and dx denotes integration over all paths. In the classical limit, the path of minimum action dominates the integral, because the phase of any path away from this fluctuates rapidly and different contributions cancel. The connection with statistical mechanics follows. Considering only paths which begin and end in the same configuration, perform the Wick rotation, that is, make time imaginary, and integrate over all possible beginning-ending configurations. The path integral now resembles the partition function of statistical mechanics defined in a canonical ensemble with inverse temperature proportional to imaginary time. Strictly speaking, though, this is the partition function for a statistical field theory. Clearly, such a deep analogy between quantum mechanics and statistical mechanics cannot be dependent on the formulation. In the canonical formulation, one sees that the unitary evolution operator of a state is given by where the state I plus or minus is evolved from time t equals 0. If one makes a Wick rotation here, and finds the amplitude to go from any state, back to the same state in time it is given by, which is precisely the partition function of statistical mechanics for the same system at temperature quoted earlier. One aspect of this equivalence was also known to Schrödinger, who remarked that the equation named after him looked like the diffusion equation after Wick rotation. Equals measure theoretic factors equals, sometimes we also have measure theoretic factors in the functional integral. This factor is needed to restore unitarity. For instance, if then it means that each spatial slice is multiplied by the measure SHG. This measure can't be expressed as a functional multiplying the measure because they belong to entirely different classes. Quantum field theory, the path integral formulation was very important for the development of quantum field theory. Both the Schrödinger and Heisenberg approaches to quantum mechanics single out time, and are not in the spirit of relativity. For example, the Heisenberg approach requires that scalar field operators obey the commutation relation for x and y two simultaneous spatial positions, and this is not a relativistically invariant concept. The results of a calculation are covariant, but the symmetry is not apparent in intermediate stages. If naive field theory calculations did not produce infinite answers in the continuum limit, this would not have been such a big problem. It would just have been a bad choice of coordinates. But the lack of symmetry means that the infinite quantities must be cut off, and the bad coordinates make it nearly impossible to cut off the theory without spoiling the symmetry. This makes it difficult to extract the physical predictions, which require a careful limiting procedure. The problem of lost symmetry also appears in classical mechanics, where the Hamiltonian formulation also superficially singles out time. The Lagrangian formulation makes the relativistic invariance apparent. In the same way, the path integral is manifestly relativistic. It reproduces the Schrödinger equation, the Heisenberg equations of motion, and the canonical commutation relations and showed that they are compatible with relativity. It extends the Heisenberg type operator algebra to operator product rules, which are new relations difficult to see in the old formalism. Further, different choices of canonical variables lead to very different seeming formulations of the same theory. The transformations between the variables can be very complicated, but the path integral makes them into reasonably straightforward changes of integration variables. For these reasons, the Feynman path integral has made earlier formalisms largely obsolete. The price of a path integral representation is that the unitarity of a theory is no longer self-evident, but it can be proven by changing variables to some canonical representation. The path integral itself also deals with larger mathematical spaces than is usual, which requires more careful mathematics, not all of which has been fully worked out. The path integral historically was not immediately accepted, partly because it took many years to incorporate Feynman's properly. This required physicists to invent an entirely new mathematical object, the Grassmann variable, which also allowed changes of variables to be done naturally, as well as allowing constrained quantization. The integration variables in the path integral are subtly non-commuting. The value of the product of two field operators at what looks like the same point depends on how the 2 points are ordered in space and time. This makes some naive identities fail. The propagator equals, in relativistic theories, there is both a particle and field representation for every theory. The field representation is a sum over all field configurations, and the particle representation is a sum over different particle paths. The non-relativistic formulation is traditionally given in terms of particle paths, not fields. There, the path integral and the usual variables, with fixed boundary conditions, gives the probability amplitude for a particle to go from point x to point y in time t. This is called the propagator. Superposing different values of the initial position with an arbitrary initial state constructs the final state. For a spatially homogeneous system, where k, x, y, is only a function of, the integral is a convolution, the final state is the initial state convolved with the propagator. For a free particle of mass m, the propagator can be evaluated either explicitly from the path integral or by noting that the Schrödinger equation is a diffusion equation in imaginary time and the solution must be a normalized Gaussian. Taking the Fourier transform in produces another Gaussian. And in p-space the proportionality factor here is constant in time, as will be verified in a moment. The Fourier transform in time, extending k, p, t, to be 0 for negative times, gives the Green's function, or the frequency space propagator, which is the reciprocal of the operator which annihilates the wave function in the Schrödinger equation, which wouldn't have come out right if the proportionality factor weren't constant in the p-space representation. The infinitesimal term in the denominator is a small positive number which guarantees that the inverse Fourier transform in E will be non-zero only for future times. For past times, the inverse Fourier transform contour closest toward values of E where there is no singularity. This guarantees that K propagates the particle into the future and is the reason for the subscript on G. The infinitesimal term can be interpreted as an infinitesimal rotation toward imaginary time. It is also possible to re-express the non-relativistic time evolution in terms of propagators which go toward the past, since the Schrödinger equation is time reversible. The past propagator is the same as the future propagator except for the obvious difference that it vanishes in the future, and in the Gaussian T is replaced by. In this case, the interpretation is that these are the quantities to convolve the final wave function so as to get the initial wave function. Given the nearly identical only change is the sign of E and I micron. The parameter E in the Green's function can either be the energy if the paths are going toward the future, or the negative of the energy if the paths are going toward the past. For a non-relativistic theory, the time as measured along the path of a moving particle and the time as measured by an outside observer are the same. In relativity, this is no longer true. For a relativistic theory the propagator should be defined as the sum over all paths which travel between 2 points in a fixed proper time, as measured along the path. These paths describe the trajectory of a particle in space and in time. The integral above is not trivial to interpret, because of the square root. Fortunately, there is a heuristic trick. The sum is over the relativistic arc length of the path of an oscillating quantity, and like the non-relativistic path integral should be interpreted as slightly rotated into imaginary time. The function can be evaluated when the sum is over paths in Euclidean space. This describes a sum over all paths of length of the exponential of minus the length. This can be given a probability interpretation. The sum over all paths is a probability average over a path constructed step by step. The total number of steps is proportional to, and each step is less likely the longer it is. By the central limit theorem, the result of many independent steps is a Gaussian variance proportional to. The usual definition of the relativistic propagator only asks for the amplitude is to travel from x to y, after summing over all the possible proper times it could take. Where is a weight factor, the relative importance of paths of different proper time? By the translation symmetry in proper time, this weight can only be an exponential factor, and can be absorbed into the constant I plus or minus. This is the Schwinger representation. Taking a Fourier transform over the variable can be done for each value of separately, and because each separate contribution is a Gaussian, gives whose Fourier transform is another Gaussian with reciprocal width. So in p-space, the propagator can be re-expressed simply. Which is the Euclidean propagator for a scalar particle. Rotating PO to be imaginary gives the usual relativistic propagator, up to a factor of and an ambiguity which will be clarified below. This expression can be interpreted in the non-relativistic limit, where it is convenient to split it by partial fractions. For states where one non-relativistic particle is present, the initial wave function has a frequency distribution concentrated near PO equals m. When convolving with the propagator, which in p-space just means multiplying by the propagator, the second term is suppressed and the first term is enhanced. For frequencies near PO equals m, the dominant first term has the form. This is the expression for the non-relativistic Green's function of a free Schrödinger paragraph Dirac particle. The second term has a non-relativistic limit also, but this limit is concentrated on frequencies which are negative. The second pole is dominated by contributions from paths where the proper time and the coordinate time are ticking in an opposite sense, which means that the second term is to be interpreted as the antiparticle. The non-relativistic analysis shows that with this form the antiparticle still has positive energy. The proper way to express this mathematically is that, adding a small suppression factor in proper time, the limit where TAAA of the first term must vanish, while the TA plus a limit of the second term must vanish. In the Fourier transform, this means shifting the pole in PO slightly, so that the inverse Fourier transform will pick up a small decay factor in one of the time directions. Without these terms, the pole contribution could not be unambiguously evaluated when taking the inverse Fourier transform of PO. The terms can be recombined, which when factored, produces opposite sign infinitesimal terms in each factor. This is the mathematically precise form of the relativistic particle propagator, free of any ambiguities. The I micron term introduces a small imaginary part of the I plus or minus equals m2, which in the Minkowski version is a small exponential suppression of long paths. So in the relativistic case, the Feynman path integral representation of the propagator includes paths which go backwards in time, which describe antiparticles. The paths which contribute to the relativistic propagator go forward and backwards in time, and the interpretation of this is that the amplitude for a free particle to travel between 2 points includes amplitudes for the particle to fluctuate into an antiparticle, travel back in time, then forward again. Unlike the non-relativistic case, it is impossible to produce a relativistic theory of local particle propagation without including antiparticles. All local differential operators have inverses which are non-zero outside the light cone, meaning that it is impossible to keep a particle from traveling faster than light. Such a particle cannot have a Green's function which is only non-zero in the future in a relativistically invariant theory. Functionals of fields equals, however, The path integral formulation is also extremely important in direct application to quantum field theory, in which the paths, or histories being considered are not the motions of a single particle, but the possible time evolutions of a field over all space. The action is referred to technically as a functional of the field, S, I, where the field I, xi 1/4 is itself a function of space and time, and the square brackets are a reminder that the action depends on all the field's values everywhere, not just some particular value. In principle, one integrates Feynman's amplitude over the class of all possible combinations of values that the field could have anywhere in spatial time. Much of the formal study of QFT is devoted to the properties of the resulting functional integral, and much effort has been made toward making these functional integrals mathematically precise. Such a functional integral is extremely similar to the partition function in statistical mechanics. Indeed, it is sometimes called a partition function, and the two are essentially mathematically identical except for the factor of I in the exponent in Feynman's postulate 3. Analytically continuing the integral to an imaginary time variable makes the functional integral even more like a statistical partition function, and also tames some of the mathematical difficulties of working with these integrals. Expectation values equals, in quantum field theory, if the action is given by the functional of field configurations, then the time-ordered vacuum expectation value of polynomially bounded functional f is given by. The symbol here is a concise way to represent the infinite-dimensional integral over all possible field configurations on all of spatial time. As stated above, the unadorned path integral in the denominator ensures proper normalization. As a probability equals, strictly speaking, the only question that can be asked in physics is, what fraction of states satisfying condition A also satisfy condition B? The answer to this is a number between 0 and 1 which can be interpreted as a probability which is written as P, BA. In terms of path integration, since this means where the functional in I is the superposition of all incoming states that could lead to the states we are interested in. In particular, this could be a state corresponding to the state of the universe just after the Big Bang, although for actual calculation this can be simplified using heuristic methods. Since this expression is a quotient of path integrals, it is naturally normalized. Schwinger Dyson equations equals. Since this formulation of quantum mechanics is analogous to classical action principles, one might expect that identities concerning the action in classical mechanics would have quantum counterparts derivable from a functional integral. This is often the case. In the language of functional analysis, we can write the Euler-Lagrange equations as the left-hand side is a functional derivative. The equation means that the action is stationary under small changes in the field configuration. The quantum analogues of these equations are called the Schwinger Dyson equations. If the functional measure turns out to be translationally invariant, and if we assume that after a Wick rotation, which now becomes for some h goes to 0 faster than a reciprocal of any polynomial for large values of I, we can integrate by parts to get the following Schwinger Dyson equations for the expectation for any polynomially bounded functional f. In the DeWitt notation, these equations are the analog of the Onshaliel equations. If J is an element of the dual space of the field configurations, then the generating functional Z of the source fields is defined to be. Note that or where. Basically, if is viewed as a functional distribution, then are its moments and Z is its Fourier transform. If f is a functional of I, then for an operator k, f, k, is defined to be the operator which substitutes k for I. For example, if and g is a functional of j, then, from the properties of the functional integrals, we get the master Schwinger Dyson equation. Or, if the functional measure is not translationally invariant, it might be possible to express it as the product where m is a functional and is a translationally invariant measure. This is true, for example, for nonlinear sigma models where the target space is diffeomorphic to Rn. However, if the target manifold is some topologically non-trivial space, The concept of a translation does not even make any sense. In that case, we would have to replace the in this equation by another functional. If we expand this equation as a Taylor series about j equals 0, we get the entire set of Schwinger-Dyson equations. Localization. The path integrals are usually thought of as being the sum of all paths through an infinite spatial time. However, in local quantum field theory we would restrict everything to lie within a finite causally complete region, for example inside a double light cone. This gives a more mathematically precise and physically rigorous definition of quantum field theory. Warder-Takahashi identities equals, see main article Warder-Takahashi identity. Now how about the Onshel-Noether's theorem for the classical case? Does it have a quantum analog as well? Yes, but with a caveat. The functional measure would have to be invariant under the one-parameter group of symmetry transformation as well. Let's just assume for simplicity here that the symmetry in question is local. Let's also assume that the action is local in the sense that it is the integral over spacetime of a Lagrangian, and that for some function f where f only depends locally on I. If we don't assume any special boundary conditions, this would not be a true symmetry in the true sense of the term in general unless f equals 0 or something. Here, Q is a derivation which generates the one-parameter group in question. We could have antiderivations as well, such as BRST and supersymmetry. Let's also assume for any polynomially bounded functional f. This property is called the invariance of the measure. And this does not hold in general. See anomaly for more details. Then, which implies where the integral is over the boundary. This is the quantum analog of Noether's theorem. Now, let's assume even further that Q is a local integral. Where? So that where? This is assuming the Lagrangian only depends on I and its first partial derivatives. More general Lagrangians would require a modification to this definition. Note that we're not insisting that Q, X, is the generator of a symmetry, but just that Q is. And we also assume the even stronger assumption that the functional measure is locally invariant. Then, we would have alternatively, the above two equations are the Warder-Takahashi identities. Now for the case where f equals 0, we can forget about all the boundary conditions and locality assumptions. We'd simply have alternatively the need for regulators and renormalization. Path integrals as they are defined here require the introduction of regulators. Changing the scale of the regulator leads to the renormalization group. In fact, renormalization is the major obstruction to making path integrals well defined. The path integral in quantum mechanical interpretation, in one philosophical interpretation of quantum mechanics, the sum over histories interpretation, the path integral is taken to be fundamental and reality is viewed as a single indistinguishable class of paths which all share the same events. For this interpretation, it is crucial to understand what exactly an event is. The sum over histories method gives identical results to canonical quantum mechanics, and Sinner and Sorkin claim the interpretation explains the Einstein-Podolsky-Rosen paradox without resorting to non-locality does represent the results of a QM experiment says that all contributions of paths close to black holes cancel in the action for an EPR-style experiment here on Earth. Some advocates of interpretations of quantum mechanics emphasizing coherence have attempted to make more rigorous the notion of extracting a classical-like coarse-grained history from the space of all possible histories. Quantum gravity, whereas in quantum mechanics the path integral formulation is fully equivalent to other formulations, it may be that it can be extended to quantum gravity, which would make it different from the Hilbert space model. Feynman had some success in this direction and his work has been extended by Hawking and others. Approaches that use this method include causal dynamical triangulations and spin foam models. Quantum tunneling can be modeled by using the path integral formation to determine the action of the trajectory through a potential barrier. Using the WKB approximation, the tunneling rate can be determined to be of the form with the effective action and pre-exponential factor. This form is specifically useful in a dissipative system, in which the systems and surroundings must be modeled together. Using the Langevin equation to model Brownian motion, the path integral formation can be used to determine an effective action and pre-exponential model to see the effect of dissipation on tunneling. From this model, tunneling rates of macroscopic systems can be predicted. See also, theoretical and experimental justification for the Schrödinger equation, static forces and virtual particle exchange, Feynman checkerboard, propagators, Wheeler Feynman absorber theory, Feynman CAC formula. References. Notes. Suggested reading, Feynman, R.P. and Hibbs, A.R. Quantum Mechanics and Path Integrals. New York, McGraw-Hill. ISBN 0-07-020650-3. The historical reference, written by the inventor of the path integral formulation himself and one of his students. Hagen Klinert. Path integrals in quantum mechanics, statistics, polymer physics, and financial markets. Singapore, World Scientific. ISBN 981-238-107-4. Zinn Justin, Jean. Path integrals in quantum mechanics. Oxford University Press. ISBN 0-19-856674-3. A highly readable introduction to the subject. Shulman, Larry S. Techniques and Applications of Path Integration. New York, John Wiley & Sons. ISBN 0-486-44528-3. A modern reference on the subject. Ahmad, Ishfaq. Mathematical Integrals in Quantum Nature. The Nucleus pages 189-209. Inomata, Akira, Kuratsuji, Hiroshi, and Jerry, Christopher. Path Integrals and Coherent States of SU, 2, and SU, 1, 1. Singapore, World Scientific. ISBN 981-02-0656-9. Grosch, Christian and Steiner, Frank. Handbook of Feynman Path Integrals. Springer Tracts in Modern Physics 145. Springer Verlag. ISBN 3-540-57135-3. Toma copyright, Wolfgang A. Path Integrals on Group Manifolds. Singapore, World Scientific. ISBN 981-02-3355-8. Discusses the definition of path integrals for systems whose kinematical variables are the generators of a real separable, connected Lie group with irreducible, square integrable representations. Clowder, John R. A Modern Approach to Functional Integration. New York, Berger Currency User. ISBN 978-0-8176-4790-2. Ryder, Lewis H. Quantum Field Theory. Cambridge University Press. ISBN 0-521-33859-X. Highly readable textbook. Introduction to Relativistic QFT for Particle Physics. Rivers, R.J. Path Integrals Methods in Quantum Field Theory. Cambridge University Press. ISBN 0-521-25979-7. Albevario, S. and Hucron. A Mathematical Theory of Feynman Path Integral. Lecture Notes in Mathematics 523. Springer Verlag. ISBN 0-387-07785-5. Glim, James, and Jaff, Arthur. Quantum Physics, A Functional Integral Point of View. New York, Springer Verlag. ISBN 0-387-90562-6. Simon, Barry. Functional Integration and Quantum Physics. New York, Academic Press. ISBN 0821869418. A Mathematically Rigorous Introduction to Functional Integration, Gerald W. Johnson and Michel L. Lapidoux. The Feynman Integral and Feynman's Operational Calculus. Oxford Mathematical Monographs. Oxford University Press. ISBN 0-19-851572-3. Ettinghoff, Pavel. Geometry and Quantum Field Theory. MIT OpenCourseWare. This course, designed for mathematicians, is a rigorous introduction to perturbative quantum field theory, using the language of functional integrals. Z. Anthony. Quantum Field Theory in a Nutshell. Princeton University Press. ISBN 978-0-691-14034-6. A Great Introduction to Path Integrals and QFT in General. Grosch, Christian. An Introduction into the Feynman Path Integral. A.R. Ziv, Hep th/9302097. Mackenzie, Richard. Path Integral Methods and Applications. A.R. Ziv, Quant Ph/0004090. De Witt-Moret, Car Copyright Kiel. Feynman's Path Integral, Definition without Limiting Procedure. Communication in Mathematical Physics 28, 47 Euro 67. Bibcode, 1972 CMA Ph 28. 47 doi, 10.1007/BF020993771. Mr. 0309456. Sinner, Sukanaya. Sorkin, Raphael D. A Sum over History's Account of an EPR, B, Experiment. Foundations of Physics Letters 4, 303 Euro 335. Bibcode, 1991 FOPHL. 4303 doi, 10.1007/BF006658892. Cartier, Pierre. De Witt-Moret, Car Copyright Kiel. A New Perspective on Functional Integration. Journal of Mathematical Physics 36, 2137 Euro 2340. A.R. Ziv, Funct and /9602005. Bibcode, 1995 JMP, 36.2237 doi, 10.1063/1.531039. External links, Path Integral on Scholarpedia, Path Integrals in Quantum Theories, A Pedagogic First Step.